Alright, welcome back. This is the college algebra videos. Today we'll be solving exponential equations. In fact, to be more specific, we'll be using logarithms to solve exponential equations. And what we're actually going to use are the following. We're going to use these three properties right here, but more importantly, we're going to use this last one. And so I want to remind you a little bit of where these kind of come from. These come from if you remember, we were doing functions and I had you graph. I said, oh, okay, here, take this function that's an exponential, a to the x. Plug in 0. Well, a to the 0, what's a to the 0? Well, you told me that was 1. Then I said, plug in 1, and you said, okay, what's a to the first? Well, that's nothing really. It doesn't do much. It's just a. And so we have this. And so then I said, okay, let's find the inverse. And to find the inverse, I said, okay, the inputs will be x, but now we call the inverse the log a of something. And so I said, well, what does it mean when the input is 1? Well, most of you know that since here this is 0, 1, the inverse would be 1, 0. You would just reverse the x and the y. And then over here, since you have the point 1a, you know that the inverse should have the opposite, not the opposite point, but the point that gets reverses the x and the y, which is a comma 1. And so this is where we got this expression. So this first line says when the input is 1, the output is 0. That's exactly what this property 4 is saying. And then here, this part of the table says that when the input is a, the output is 1. Well, that's what this is saying. When the input is a, the output is 1. And so that's where number 5 comes from. Well, I'd like to show you where letter 6 comes from. There's two ways to look at it. One way is to say, okay, what if the input is x? Then the output must be to the a to the x. So here, when the input is a to the x, the output must be x. And that's exactly what this is saying. When the input of the log is a to the x, the output should be x. So this is one way to look at this. A different way, which I kind of like, because it kind of connects everything I hope for you, is that let me start with the left-hand side. I have log a to the ax. Well, you have just learned a property, I think it's property number 2 in previous videos, that this x, because it's a power, can go on the front. So that means I can rewrite this as x times log a of a. But you see, property number 5 says that if you have the log a of a, you can replace this with a 1, which means that here I can write this as x times 1, and x times 1 is x. And that's exactly what this property is trying to tell us. That whenever you have a log, if your input is a to some power, whatever the power is, that's actually the output. Okay, so this is going to help us in solving. Go ahead and look at an example. We're going to solve the exponential function. And again, they're going to ask us to write the answers in exact form and also to approximate up to 4 decimal places. So let's start by solving this. The first thing, let me write down some steps. One of the first things that you want to do is you want to be able to isolate, let me use red instead. Isolate the exponential. Okay. So what that means is that here in this problem, we're going to try to get e to the 1.5x all by itself. So I need to subtract this 3 because we don't want the 3 there. And so when I subtract the 3, I get that this is gone. I get negative 8 e to the 1.5x, and I know that negative 1 minus 3 is negative 4. Now we know that if we want to isolate here, the nicest thing to do is to divide by negative 8. And so I get that e to the 1.5x equals to 1/2. Now, what I want to use here is I want to use the fact, actually what we say, we say take the natural log of both sides. In fact, if you've taken this before, you should have heard this expression before. Take the natural log of both sides. So what does this mean? Well, this means that what we want you to do is take the function that's the natural log and as an input replace e to the 1.5x. But the fact that you have this equal sign means that when you input e to the 1.5x, that's the same thing as inputting the 1/2. And so now what you're allowed to do is use this property that I just went over. I said that whenever you have a log to the base and you have a to the x, you're going to get x. Well, for natural logs, that looks like this. Oops, and this base is e, sorry, the base is z, you're going to get x. Because remember, the natural log is really log base e, so this is where this is coming from. And so what that means is in this problem is that this 1.5 is sort of like the input, and these will be gone. And so what I'm left with is 1.5x equals the natural log of 1/2. Okay, now all I have to do is solve for x. Now, usually I would say divide both sides by 1.5, but the problem is, well, it's not that it's a problem, but you're going to get an answer that doesn't look too nice. Natural log of 1/2 divided by 1.5. And this is okay, and you can write this. But instead, I'm going to write the 1.5 as 3/2. And the natural log of 1/2 as natural log of 1 minus natural log of 2, using my rules of exponents. Well, remember the natural log of 1 is 0. This is property number 4 in the previous slide. So I get that 3/2 x is equal to negative natural log of 2. And now what I like to do is multiply both sides by 2/3. And so what that gives me is that these cancel, and I get that x is equal to negative 2/3 natural log of 2. Now, this answer up here is correct. This answer down here is correct. They're both okay, but this one's, the bottom one is the nicer one. This is the one that I like, but it's not going to matter. You just have to know that they both mean the same thing. Now, finally, the book does ask for us to approximate, so you want to double check my work, but according to my calculations, x is equal to negative 0.4621. Okay, let's try another example. So again, if you after this example, feel free, try it on your own. Okay, welcome back. How would I do this? Well, I would subtract 23 first, because I want to, remember, I want to isolate 10 to the 3x. So let's subtract the 23 first. So I get 50 equals 10 to the 3x. So that's the isolate part. That was step number 1. Now I want to take the common log. So this is the take. Sometimes it should say the log, but it should really be the common log. And what that means is that you're going to say, okay, well, let me take the log function, the one that's base 10, but remember we don't always write that base 10, and put as an input 10 to the 3x. But again, these two numbers up here, these two expressions mean the same thing. So that's the same thing as plugging in 50 into the log. And this we can do with our calculator. We will. This is a calculator function that we're going to do later on. But remember, I want to solve. And so what happens is now I use the property that I mentioned before, that when you have the bases matching, that you're just going to get x. And that's exactly what I have here. I have the bases matching. And so I get whatever the exponent is, and the exponent is 3x. So 3x is equal to log 50. And now when I divide by 3 on both sides, because I want to get the x by itself, that's always our goal, so I divide both sides by 3, and so the exact answer is x equals log of 50 divided by 3. This is something you can plug into your calculator so that you get that x is approximately equal to 0.5663. Okay, so hopefully that makes sense. We have one more example, and then we'll let you try. Okay, so try this one first. Okay, welcome back. Let's isolate. So the steps are all the same here. Let's isolate this. So let's subtract 18 from both sides. That cancels. So I get 20 e to the 0.2x minus 1 equals 16. Let me divide by 20 on both sides. This is very nice. This is gone. So I get e to the 0.2x minus 1 equals 3. All right. Now I'm going to take the natural log of both sides. Remember, that's how we say it. So take natural log. All right. So we take the natural log of both sides. And those of you who took high school math, this is probably the part you remember. Again, what's going on here is that the natural log of e to some power is just going to be that power. This power will be here, so this is what we're taking, that power in there. So we get that 0.2x minus 1 equals the natural log of 3. I want to solve for x, so let me add 1 to both sides. I get 0.2x equals the natural log of 3 plus 1. I'm going to, again, switch the way I look at things. To me, 0.2 is really 1/5 x. If you don't believe me, plug in 1/5 into your calculator and you'll see the calculator returns 0.2. So to solve this, I'm going to multiply both sides by 5. And so on the left, I get x, and on the right, I get 5 natural log of 3 plus 1. Some of you might have a different answer. You might have had it divided by 0.2. That's correct. So if you had, some of you might have the natural log of 3 plus 1 divided by 0.2. That's also correct, but I think that my version looks a little bit prettier. But that's eyes in the, beauty's in the eye of the beholder, right? So it doesn't matter. It won't matter. And then finally, the approximate form. Again, check this work with the calculator, but I got that x is approximately 10.4931. All right, this is what we have. This should help you with your homework. Good luck, and if you have any questions, let me know.